Welcome back, everyone. This is Stuart Mitchell again. I hope everyone's doing well. We're going to continue along with Lecture 5, which is considering operations with fractions and variables. These operations we're talking about are addition, subtraction, multiplication, and division, the standard mathematical operations that you've worked with and that you know. This time, we're just doing them with fractions instead of just integers. Some of these fractions have variables. Some have positive and negative numbers. We're going to be applying a lot of the same things that we've been talking about in the previous lectures here, kind of bringing them all together when considering them with fractions. Okay, so the first thing we can talk about here is addition or subtraction, because even though they're different operations, they go together, like addition and subtraction. In terms of with fractions, like it's relatively the same process with how you have to go about it. So we're gonna talk about that. Okay, so in general, when you are adding or subtracting fractions, and in order to emulate that, I'm going to talk about plus or minus. That means you either add or subtract, because it's going to end up being the same either way. This, or not like the same result, but like the same process either way, I should say. So if you consider two arbitrary fractions, we'll call them a over b, and you're either adding or subtracting that to another different fraction, say c over d. We have to make a common denominator first. And if b and d are two different numbers, then they can't just be combined. Like, we can't add these together. Like, you always have to have a common denominator when you're adding or subtracting fractions. So in order to do that, we have to make these the same somehow. And then to make these the same denominator, we're going to multiply this fraction by d on the top and bottom. And then we're going to multiply this fraction over here by b in the top and bottom, or numerator and denominator. And the reason for that is just the rule, like whatever you do to the denominator of a fraction, you have to do to the numerator as well. And you do that because like when you think about d divided by d, it's a number divided by the same number. So that's going to give you 1. Same with b over b. This is essentially, this and this is essentially like multiplying by 1. So it doesn't change the value of the fraction. It just changes how it looks so that you can, changes how it looks so you can combine them as necessary. So if we multiply d and a together, we're just going to have a d. And then b and d together, we're going to have over bd. And then we keep this plus or minus. And then similarly over here, we're going to have bc over bd. Okay, so when you're adding or subtracting fractions, I know it seems weird, but you're only going to add and combine the numerators, and the common denominators are going to stay the same, which is why you need a common denominator when you add and subtract fractions. So you're going to end up with AD plus or minus BC in the numerator, and then your new denominator for everything is going to be BD. We'll do a quick concrete example with that just to kind of make it, because it seems kind of hard to consider it with all these variables. That's the general way to do it. So if you're thinking about this, say you have like 1/7 plus 2/6. Actually, I'm sorry, that's a bad example because you can reduce that fraction. We will just reduce that fraction. We'll say plus 1/3. Now we can't just add these together as is, because we don't have a common denominator here. So we don't know like how much of a whole we're talking about, and like the reason we have to think about it with a common denominator is because when you're adding fractions together, like when you're adding them to each other, you're you're thinking about it as like you're adding parts of a whole together. So when you're adding them, you have to consider the same parts, or like, parts of the same whole, or else it kind of makes it meaningless because you can't really say anything about that. Like 1/7, like that's like when you divide one into 7 parts. 1/3 is when you divide one into 3 parts. So they're different in size. You can't really say much when you're just adding them like this. You'd have to consider them as both being part of the same whole, in order to make any kind of like natural sense about that. That's why when you're adding or subtracting fractions, or fractions, if you think of them as parts of a whole, you have to think about them as the same part, or the parts of the same whole. Which, just to kind of drive the point home, we want to think about them as parts of the same whole. And to do that, we look at common denominators. So in order to think about these with common denominators, like we have to think about if these things like share any factors, to see what's like missing from each side. These don't share any factors with each other. 7 and 3 like don't have any like similar things about them. So what we're gonna do, I'll rewrite this down here just for more room. As we did up further, we're going to multiply this side by 3/3 and multiply this fraction by 7/7. So when we multiply these two together, across, so when we multiply the numerator and denominator together by these, that's what we're doing over here. We're multiplying the numerator and denominator by the same number. We're going to end up with 3/21 plus 7/21. If you reduce these fractions back, and essentially just did the, oops, sorry, that completely messed that up. If you do the opposite of what we just did, you'll end up with the same equivalent expression as before, which is what we want. You'd end up with 1/7 plus 1/3 if you reduce these fractions. But now what we have is parts of the same whole. We're considering 3/21 and 7/21. We're talking like they're, each 21st is the same size. So we're just considering like two groups of, like two parts of the same whole, which is what we wanted to do. And now, as we did before, the whole is the reason that the denominator stays the same when you're adding is because the whole that you're talking about, like, 21 21/21 or 21/21, that whole, when you're adding back towards 1, isn't going to change. Like, you're not changing it to a different part of a whole. You're just grouping together more parts of that whole. So you only consider the adding the numerators together, or subtracting the numerators. In this case, 3/21 plus 7/21 would be 10. Oops, sorry, that didn't go as planned quite. 10/21. Because like you're considering those parts of the whole, like three of them and 7 of them will give you 10 of them. And that would be our final answer. Just like, a concrete example to kind of help you visualize what was going on, because it's a little harder to gather from this. Subtraction works the exact same way, except you just subtract instead of add. The next part, which multiplication and division of fractions can be thought of really similarly, but they're tiny, like the process is a tiny bit different, so I'm going to consider them separately for a moment. Okay, so Part 2. Part 2 is multiplication. So if you consider any two fractions, arbitrary fractions, a over b times c over d, all that you do, which is essentially what we did up here, is in this area and this area right here, is you just multiply straight across the numerators and denominators. You would multiply, yeah, I get a different color for this just to demonstrate. You multiply straight across the numerator or the numerators to create a new numerator, and you'd multiply straight across in the denominator to get a new denominator, to get the new one. So you'd end up with AC over BD. It's the same exact process as we employed above. When you're multiplying two fractions together, you multiply straight across, because the multiplication applies to the numerator and denominator, because you're multiplying different parts of different wholes. Like you're not considering the same thing. You're just multiplying different parts of different wholes together to get a completely different result. So you'd have to multiply straight across the numerator, straight across the denominator to get that. So like a concrete example of this would be, is there a different color? Like 3/4 times 5/8. You're not adding these together here. You're not considering the same exact thing. Like you're not saying, like what's 3/4 plus 5/8 or 3/4 minus 5/8. You're not talking about like adding or subtracting to like group like different parts of the same whole together. You're seeing what would happen if you multiplied different parts of different different fractions together. So you have to consider how the denominator would change with that too, because you're going to end up with something completely different. So you're going to multiply straight across and straight across in the numerator and denominator. So you'd end up with 3 times 5 over 4 times 8, which would give you 15 over 32. And that'd be your final answer for that. Just as like a nice quick concrete example, the last operation to consider is division. And especially in the case of fractions, multiplication and division are very closely related, simply because when you're considering two fractions, a over b divided by c over d, the convention here is to multiply by the reciprocal, because when you're dividing by these, it doesn't work the same to divide across. That doesn't really you can't really do that when you're dealing with fractions here. So you'd have this turns into a over b times d over c. You multiply by the reciprocal. And the reciprocal just means when you flip a fraction over, when you interchange the numerator and the denominator. And that would be, it's the reciprocal of c over d would be d over c. And then you just carry on with the multiplication as normal. You multiply straight across both then, and you end up with a over b. I'm sorry, that AD over BC. And I will show you in a concrete example why that's the case, because you might be thinking well, why do you just randomly do it when you divide? well, I can show you how to, or like what you would do for that. Okay, so let's say we have like 1/3 divided by 2/5. The standard convention here is to do 1/3 multiplied by the reciprocal, which is 5/2. And then you just multiply straight across like we did before, which would be 5/6. And like you can take or leave this part if you care, care why this works at all. You don't really necessarily have to for this. You just kind of have to be able to do it and just remember the rule. But if you want to take this sidebar with me to see why it works the way it does, if we consider the initial 1/3 divided by, I'm sorry, that wasn't right. That was supposed to be a 2. Divided by 2/5, that can be the same thing as writing like a complex fraction, which is 2 fractions over each other. 1/3 over 2/5. Now, in order to get this out of the denominator, this fraction 2/5 right here, in order to get that out of the denominator, you'd have to employ the same kind of, oops, sorry, let me fix that 3 because it's a little hard to see. You'd have to employ the same logic we did when we were adding and subtracting to create a common denominator. And whatever you do to the numerator, you have to do to the denominator or vice versa. So to clear this 5 out, since we're dividing by 5 here, we'd multiply by 5. And then we'd also have to multiply by 5 up here to keep it consistent, so we could cancel these and it'd be equivalent still. But these are going to cancel each other out. And then we're going to be left with 5/3, 1 times 5/3 all over 2. And then to get rid of this 2, since we're dividing by 2 here, we can think about that as like we're dividing by 2, but if we think about this, that's really like if we're dividing this, we should put this where the division is in the denominator since we're dividing. So we'd end up with 1 times 5 over 3 times 2, which is exactly what we did up here. But that's just, that's the kind of like the logic behind why it works. Which then would be 5/6 again. Alternatively, I guess like another way to think about that, if you're on the train of caring why this is the case, if you thought about this same example again as 1/3 divided by 2/5 and thought about it like a fraction again, we could turn it back into that complex fraction 1/3 over 2/5. But when you're thinking about this, if you were to factor out this 1/3, you'd have 1/3 times 1 over 2/5. And in the same regard as before, to like fix this, we could multiply by 5 in the denominator and again in the numerator. That would cancel these 5s here, but then we'd be left with 1/3 times 5/2, which equals 5/6. So you get the same answer. It works. I just wanted to show you why it works for anyone who's interested in why it works. This is why. because you're essentially thinking, when you're dividing by a fraction, you're essentially thinking about it like this. Like you're doing 1/3/2/5. And if you were to take that first fraction out and replace it with a 1, you'd have like 1/2/5. So when you fix it, so you don't have a complex fraction anymore, you end up with the reciprocal. Like one divided by a number is that number's reciprocal. In terms of fractions, that would just result in you flipping the numerator and denominator over. You'd flip them, so you'd end up with 5/2. Sorry to go on that long tangent. I just figured if anyone was interested in why that was the case, instead of just taking it as a rule, sorry, that's probably just the math school coming out of me, because that's what we've had to do for so long, is just, think about why things are the way that they are. If you're not concerned, don't worry about it too much. Just remember the rule. When you're dividing fractions, multiply by the reciprocal, flip the second fraction over, multiply straight across, call it a day. If you're interested in why it worked, here's the explanation. Okay, and with that, I think we are ready to get through these examples. Just like that. Sorry that took so long to get here, but here we are. I figured that was, it could be helpful if you were interested. And also, don't discredit anything that you've learned before, because it can be really helpful. Like that, especially the stuff that you started doing in that we did in the previous lectures, because it's definitely going to come back. So when we're considering the first one, we can do a little bit of simplifying at first, because if you think about 5/8, that's like saying -5 over -8. That's the same thing as saying -5 divided by -8. And if you recall from the last lecture, when you're dividing two negative numbers, you're going to get a positive number. Or in other words, you can cancel these negatives and you're left with then just a positive 5/8. So then you'd have -4/11 times positive 5/8. And then you just multiply straight across the numerator, straight across the denominator, which then gives you -4 times 5. It's a negative times a positive. It's going to give you a negative number. Then 4 times 5 is 20, so it'd be -20/88. And as is conventional for fractions, you always want to write them in simplest form. We know that 20 and 88 both share a common factor. And if you can't think of the maximum common factor for that, like all at first, don't worry, you'll be able to see. So I know that the greatest common factor they share is 4. But if you didn't know that, you can hopefully obviously see that they both share the common factor of 2, because we know they're both even, so they at least have to both be divisible by 2. So we'll divide them both by 2 to get -10/44. But you can still simplify that. You can still see they're both even numbers. They're both divisible by 2 again. So we can definitely do that again. So this would then give you -5/22, and that's simplified. Another way to see that without doing all of the simplification at the end is this step is still the same, but if you consider up from this step and you have -4/11 times 5/8, when you multiply them across and they're all one single fraction, you're gonna be able to potentially cancel common factors that way that they would share. That's essentially what we did here. We just divided this 4 out, but we can do the same thing up here. You see a 4 up here in the numerator and an 8 in the denominator over here. Whenever you're multiplying fractions together, and that just goes for the multiplying, you can cross cancel, is what we call it. So you can cancel the like terms, which means we see that 8 and -4 both share the term 4. So you can cancel this 4. That would just become a 1. You can cancel a 4 out of here, or you can divide a 4 out of here, and that would just become 2. So then you'd be left with -1/11 times a +5/2, which when you multiply straight across the numerator and denominator gives you a -5/20, which is already simplified down like we did over here. It's just, it doesn't require as much thinking about simplifying. If you are able to cross cancel, then you can. If you're not, then you're just kind of have to go with it and see if you have to simplify later anyway. But generally, if you can't pretty much always, if you can't cross cancel, you're not going to need to simplify it later. Okay. So moving right along to the number 2, we have 2/3 times 4/9. It's just two positive fractions multiplied together, no big deal. We can just multiply those straight across. We see, if you look across this diagonal, 2 and 9 don't share anything, 4 and 3 don't share anything. We can't cross cancel, so cool. We just this is going to end up being 2 times 4 over 3 times 9, so it'll just be 8/27. Nice and simple. We're all done. That's all there is to that one. Similarly to as in my examples, like as in the multiplication, we're multiplying here. We're multiplying here. We have variables. In my example, when you multiply variables, you just multiply them together and group them together. So that's all we need to do. As you've seen in previous examples too of just multiplying variables together, you just group them and call it a nice day. And this is just multiplying. Here we don't see any negative signs. So that's cool. We don't have to worry about any negatives. We don't, these are all, except for 4, they're all variables, so they don't share any common factors, so we don't have to worry about that either. So this is just going to be b times c over 4 times d, which is just going to be bc over 4d. And that's all there is to it. We can't simplify that anymore because they're all variables. We don't know if they share anything because we don't know what they are. That's all you can do. That's as simple as it gets. And we can move on. Oops, sorry. Got a little trigger happy there with that. Okay, so moving on, we have 3/7 divided by 9/10. So we employ, actually before I switch to the pen again, we employ rule number 3. When you're dividing fractions, you multiply by the reciprocal of the second fraction. So in this case, in this case, we are multiplying by we're going to be multiplying by the reciprocal of 9/10. Because we're switching that one, the second fraction. When you're dividing, you always multiply by the reciprocal. When you're dividing two fractions, you always multiply by the reciprocal of whatever is on the right side of the division sign. Or like in the case of number 5, whatever is on the bottom of the fraction bar, the denominator. Like that's what you would multiply by the reciprocal of. So we can think about this as 3/7 times 10/9. Like I said, the reciprocal just means you interchange the numerator and denominator. We can check for cross-canceling. Any things that'll cross-cancel here to make the end easier. 10 and 7 don't share anything, but 3 and 9 do. Namely, like 3 can come out of 9, 9 can be divided by 3, and 3 can also be divided by 3. So when you do that, this becomes 1, and this becomes 3. So your resulting multiplication turns into 1 times 10 over 7 times 3, which equals 10/21. And that is all there is to that. We just have to do that. Okay, So they're trying to kind of pull a fast one, so to speak, on you in this one. But that's partly why I wanted to go through my big explanation, because this still represents dividing fractions. So if it helps to visualize it more clearly, we can think about this as 11/20ths divided by, because that's what this middle fraction bar stands for, is divided by 9/10. Again, employ rule of 3 of the division, where you multiply by the reciprocal of the second fraction, and then this would be 11/20ths times 10. Oops, sorry, that was not what I wanted to do. I'm going to try writing that again just to make sure it's better. Times 10/9. Once again, we're going to want to see if we can cross cancel anything to make our lives easier moving on. 11 and 9 don't share anything, but 10 and 20 do. 10 and 20 are both divisible by 10. So when you do that, 10 becomes 1, 20 becomes 2. When you divide by 10, because you can cancel those out. So the result would be 11 times 1, then over 2 times 9. So your final result is 11/18. Okay, sorry, once again, some of the text got omitted from this, from these documents when I tried to upload everything. For both 6 and 7, both 6 and 7, there should be the question, true or false. We're just looking to see if those are true or false. And like I had mentioned in the previous lecture, when they ask you whether things are true or false, you're going to want to evaluate them yourself first and see if you get the same answer. So if we do that for number 6, we're going to be evaluating 5/11ths plus 4/11ths. Which is nice because we already have a common denominator. We don't have to figure one out. So if we employ rule 1, which was for this, find a common denominator, that's already done. So then you keep that same denominator as we did here and only add the numerators together. Only add the numerators together. So that would, we'd keep that over 11, and 5 plus 4 is 9. So it'd be 9/11. They said 9/22. You don't ever add the denominators together, as we discussed before. You just add the numerators together. So this one would be false. Okay, 7, similarly, we are going to evaluate that ourselves to make sure that we get the same answer as them to determine if it's true. If we don't get the same answer as them, then we can determine that it's not true. So we're going to evaluate 7 minus 11/30. Which, keeping in mind too, it's nice they gave us we don't have to evaluate any kind of common denominator situation because we already have one. They're both over 30. So then that would, we'd keep the denominator, but then we'd have 7 minus 11. And as we discussed in the lecture where we're adding and subtracting sign numbers, that 7 minus 11, you're going to count back from 7. You can also think of that as, 7 plus -11 or -11 plus 7, however you want to think about that and do it. And any way you think about it, you're going to get -4/30, which is not +4/30. So this is also false, which, we can see. So just to reiterate, whenever you are asked a true or false question with some kind of computation involved, do that computation yourself. Make sure that what they're trying to tell you checks out, and go from there. Okay, so now we have 3/8 plus 1/6. Sorry, I realized I was about to use the same color as over there and don't want to do that. We have 3/8 plus 1/6. We're just adding two positive fractions together, but they have different denominators now, so we have to fix that. Let me write that a little bigger so we can see that we have 3/8 plus 1/6. So as in rule 1, we need to remedy this because we can't go anywhere as of right now. So what we're going to do, in this case, since 8 and 6 share the common factor of 2, we just have to think about what their least common multiple is, like the smallest number that they both can be multiplied to get to. Because rather than multiplying 8 times 6 and getting to 48, which we'd have to simplify later, we can do that and just multiply them straight away. Which I can do like in the first, just to show that it still works. But then I'll also show you the way where you think about their least common multiple. So we can multiply this by 8 over 8. We multiply this by 6 over 6. And then we'd end up here with 18/48 plus 8/48, which equals 26 over 48. Both of these are even, so they're both divisible by 2. So then when it's reduced into simplest form, we have 13 over 24. As I had mentioned before, if it seems confusing, don't worry about doing it this way. And since we are done with this example here, I'm going to erase it to show you the other way you can think about this if you so choose. If it's confusing, don't worry about it and just do it the way we did and then simplify at the very end. Okay, so, but although an alternative way to think about this could be, we have 3/8 plus 1/6. 6 and 8 share the common factor of 2. So we just have to think about what's the smallest number that we can multiply them, both into. If you multiply 8, you'd get times, 1, it's just 8, but if you multiplied it by 2, you'd get 16, but 6 doesn't go into 16. Whereas if you multiply 6 by 2, you'd get 12, but 8 doesn't go into 12 evenly. So if we multiplied 8 by 3, we'd get 24. We also know that 6 goes into 24. 6 times 3 is 18, though, but we know 8 doesn't go into 18. So 24 then is like the smallest number that we can get them both to go into. So we know now that we need the denominator to be 24. So you have to think about what numbers do I have to multiply each fraction by respectively to get the denominators to equal 24. Well, in this case, it'd be 4 over 4, because 6 times 4 is 24. In this case, it'd be 3 over 3, because 8 times 3 equals 24, and you'd end up then with 9/24 plus 4 over 24, which is 13/24, which we ended up with before too. Which, like I said, if that seems like a little bit too confusing to think about it like that, we'll eventually, get to a formal practice with, the greatest common factor and least common multiples and all kinds of things like that. If that seems too confusing and you don't want to do it that way, feel free to just stick with what we did here. It works the same exact way. The only thing is you just have to simplify it at the end. But then you just multiply. You don't have to think about this method over here. You can just follow method 1 for the addition or subtraction and go straight along from there. Okay. So when we're thinking about 6 over x minus a negative 4/9, we can apply a rule that we learned before from the third lecture, from adding and subtracting sign numbers, to simplify this down just a little bit more before we start. So we'd have minus a negative is plus a positive, so we'd have 6 over x plus 4/9. So we can work with positive fractions. And then we apply rule 1 again, which is where we multiply to get the denominators to be the same. So over here, we'd have to multiply by 9 over 9. Over here, we'd have to multiply by x over x. Let me scroll down just a little bit more so I can continue this along. Okay, so then we'd have 9 times 6 is 54. So we'd have 54 over 9x plus 4x over 9x. So then we'd have just, we'd keep the denominator the same as before and just add the numerator, which would be 4x. Sorry, hold on, let me rewrite that because my stylus started kind of crapping out on me here. And those look very, very similar. We'd have 4x plus 54 over 9x, and that'd be our final answer here. Okay, once again, number 10 should have the true or false question attached to it. I apologize. Some of the original things got away, or the original typing got away from me when I typed up all these worksheets. It was late at night, I was just going through it, going through the motions. I forgot some of the true or falses, and some of them just didn't carry over when I uploaded them here. So in this case, we're considering all variables, but it's saying true or false. Negative z over xt divided by positive z over xt is equal to -1. Well, there's a few different ways you can kind of think about this conceptually without having to do a ton of work. We know that z over xt is equal to z over xt, and we also know that when you divide two of the same numbers, like when you divide a number by the same number, you get 1. And then if there's a negative attached to it, like there is, then you'd get -1. So that would make it true. But if you want to verify that for yourself, which is probably, better too, just to check and for the practice, we have negative z over xt divided by positive z over xt. We're calculating this for ourselves, as is conventional when they're asking you a true or false about a computation. So this is the same as multiplying by the reciprocal. Dividing is the same thing as multiplying by the reciprocal. So we have negative z over xt times xt over z. Now that we're multiplying fractions again, we can cross cancel. Z and z are the same number, so they're divisible. It's divisible. So you're going to be left with 1s. Xt and xt are the same number. They can, you can divide xt by itself and give 1. So you're left with -1 times 1 over 1 times 1, which is just -1. So this one, we finally get one that is true. That concludes lecture 5. I hope that was helpful. And thank you for listening, and I will talk to all of you next time.